Okay, so similar to yesterday, this note has a considerable amount of theory, and then what we're going to do at the end is a summary of the different types of solids, and then we'll do an example that sort of mimics the homework questions from the textbook. So the worksheet has questions about properties, and then the textbook has questions about if you were given different elements, predict what kind of solid could be formed. So we are really going to really basically scratch the surface. You can do actually a considerable amount of math with this. So if you continue in chemistry for science students in university, not like nursing or something like that, you can actually calculate the distance between atoms in a solid and use that to predict the type of solid formed. So it can get a bit more complicated. So we are going to look at what kind of forces, so inter and intramolecular, and that is why we had to review that yesterday. So then we will look at, is it dispersion forces, is it ionic bonding, is it covalent bonding, or whatever, in order to figure out what kind of solid. So there are two very broad categories, amorphous and crystalline. So amorphous is lack of order, indistinct shape. Glass and rubber are examples. So you could have dark glass, you could have clear glass, you can have frosted glass, you can have stained glass. Very unpredictable. So basically after this slide, this is it. This is the only time we're going to talk about it. Same thing with rubber. You can have all different kinds of rubber. Rubber that's in an eraser, rubber that's in a tire, and even in tires, you can have snow tires, you have all-season tires, right? So all different kinds of rubber. So again, they lack order in their arrangements, which makes them difficult to predict. So we are not going to include them after today, or after this slide. We are going to focus more on the crystalline solids because they have distinct shapes and can be organized into categories and are a bit more predictable, which makes it easier for us. So atomic, molecular, network, ionic, and metallic. And most of them are going to be easy to predict based on their names. Ionic solids have ionic bonds. Shocking. Metallic solids have metallic bonds. Molecular solids are molecules. The atomic and the network are maybe things you haven't considered before. Okay? So atomic solids they do have individual atoms as their particles held together by dispersion forces. We talked yesterday about dispersion forces or London forces, whatever, being the weakest. And we talked about if you have a weak force, then a low amount of energy is needed to break them, which means they have low melting and boiling points. And when you think about the example we used, which is noble gases in the solid state, even that phrase or that statement seems weird. Noble gases as a solid, we don't usually consider gases to be solids, but if you could decrease the pressure and temperature enough, could it become a solid? So these noble gases like argon, we would normally consider them to be gases. If we can force them to be in the solid state, then they would make this kind of cubic structure. So again, depending on how far you take chemistry, then you can actually calculate the distance here, and it does form a regular cubic repeating pattern. I'm not going to ask you to draw this, but just so you get the idea, okay? So what do you need to know? Atomic solids have atoms as their particles. That makes sense. And the force between the particles is dispersion forces, which is weak. So they have low melting and boiling points. And the next one is molecular solids, which are made up of molecules. The only problem is there are different kinds of molecules, right? So we have nonpolar and polar. So there is a distinction. So when you have a nonpolar molecule making the solid, then again, it's going to be weak dispersion forces. So something like solid methane. And even the idea behind that, you're like, what, Ms. Todd? It's not, we don't think of it as a solid. We think of it as a gas. And yes, because it has such weak forces that it's super easy to get it to change into a gas. Same thing, even with the ones that are polar, even water, which is hydrogen bonding, it is, yes, it'll make ice, but if you put an ice cube on your hand, the warmth of you, the warmth of the room would change it into a liquid and then a gas. And then you could boil it to change it into a gas. So compared to when we talk about ionic solids, these are still weaker than the intramolecular bonds. So if the molecules are polar, okay, so you can have polar. We have to do the same thing as you have done in the past. Polar molecules could be either hydrogen bonds or dipole-dipole. So we should make the distinction. So water is polar and can hydrogen bond. Something like carbon dioxide is polar, but has no hydrogen for hydrogen bonding. It would be dipole-dipole or dipole. So dry ice is solid carbon dioxide. It actually sublimes, right? So it would change into a gas. It skips the liquid phase. So they do not conduct electricity. Their electrons are held tightly. So when we talk about metallic solids, for example, like transition metals, we used the word delocalized yesterday and mobile. So the electrons can move around, allowing a current to conduct or pass through. Because their electrons are tightly held, they do not conduct. So when you do the worksheet at the back here, then you're going to choose that they have low conductivity, okay? So the next one, is weird because we call them network solids, and they are atoms, not molecules, but they are bonded covalently, which are very strong because the covalent bonds are very strong. And within the network solids, they do have a wide variety of properties, but it is atoms and they are covalently bonded. So when you have atoms that are able to covalently bond with themselves, then that is a very unique column or group that we often have skipped before. So the column that contains carbon, and then the element underneath it is silicon. Because they have such a weird valence structure, they have 4 valence electrons, then they can do strange things. so they can bond with each other, and again, it's going to form the whole next unit covalent or carbon base. But silicon can make network solids as well. So the next slide has pictures, and not that I expect you to memorize them, but just to give you a visual idea. Actually, the next 3 slides, Brenda. Okay, so this is trying to show you diamond and graphite. So both of these are carbon only. And they are both network solids because they have covalent bonds. It just is the number of covalent bonds that they have. So graphite is represented here, and it's got rings, okay, so hexagons, and they are also connected in sheets, but they don't have cross-links like diamond does. So diamond also has sort of a hexagonal structure, and it's kind of got sheets as well. There, okay, so you can kind of see it's a bit like sheets or levels, but they have extra cross links, okay? So yes, there is a repeating pattern, but you can see these extra cross links make diamond hard, the hardest substance on Earth. Graphite is what is in your pencil. I know we say lead, but it's not lead, it's actually graphite. And because it's organized in sheets, then it can be sharpened, it can be manipulated. It is a little bit softer, no, a lot softer than diamond. And diamond has been put under so much pressure to compress it that it makes it much different than graphite visually as well. You know, diamonds are a girl's best friend. They're nice and shiny, or not shiny, sparkly. Sometimes they kind of look white, or they can be pink or yellow based on the amount of pressure they've been put under. So very, very different, but the same atom only. So when you get a question that has Si or silicon or carbon only, then you're going to get a network solid. The only weird case is sometimes you might get a question with that's called a silicate. This is silicon plus oxygen. Then that is still considered to be a network solid. But when you have carbon-based network solids, it's only carbon. Another thing that is actually starting to become a little bit more common, or if you're into an area, and you can actually apply to this as a university program, it's called nanotechnology, and they are based on one of the best ones they're trying to work with, because we are carbon based, is called carbon nanotubes. Which is based on the structure called a buckyball. And why is it called a buckyball? Because it's named after a person with the unfortunate name of Buckminster Fullerene. Yeah. But they gave him props, they called them buckyballs. And when you connect a whole bunch of buckyballs together, then you get this carbon nanotube. And what they're trying to do is actually make carbon nanotubes into space. They're trying to make carbon nanotubes as opposed to plastics, which are also carbon-based, but they are also very persistent in the environment, whereas carbon nanotubes are a little bit more environmentally friendly. Yeah. Because we're trying to do everything that we're trying to do is sort of with the idea of the environment in mind and safety. So you think about now space travel. Can we travel to space? Sure. Can we travel to space without using a lot of fuel? No. Can we travel to space without spending billions of dollars? No. Can we travel to space perfectly 100% safely? Also no. So a carbon nanotube can connect us to space without actually going to space. So, but then the idea that is nanotechnology the best? Maybe you've seen the new James Bond movie. And is James Bond science? No, it is not. But definitely they're talking about the nanoscale. So again, it's all kind of emerging science. When we're done the note, we're going to watch a video about, a short clip about buckyballs and what they're trying to do. Now, the biggest thing they're trying to do with carbon nanotubes is to replace plastic, really. Space is sort of like the ultimate frontier, right? So is that an application that they're hoping is going to work? That we can create these carbon nano ladders that can connect us to, satellites or the moon. Maybe not space travel like to Saturn, but definitely closer things to Earth. That's what they're trying to do as well, okay? So obviously the applications of graphite and diamond are many. If you're a golfer, you might have graphite as your preferred choice of club. Okay, so there's recreation, graphite is, and different forms of graphite are used in safety as well, like Kevlar is cross-linking of carbon-based structures to make bulletproof vests and bulletproofing in vehicles and all that kind of stuff. So there is plenty of applications of this, and obviously diamonds as well. They use lasers that have diamonds, all kinds of things. So they are very hard and they have very high melting points because they have covalent bonds. And covalent bonds are intramolecular, so they are very, very strong. So the electrons are still not free to move. So we would consider the solid to be a non-conductor. There's also no ions as well, so even in a solution, these should not be conductive. Okay. And then an ionic solid, this one's easy. An ionic solid has ionic bonds. Wonderful, okay? And so they follow the same ideas with ionic bonds. You need ions or a metal and a non-metal, plus minus, very, very rigid. They have a very organized crystal lattice structure. They do have different charges. So you could have an aluminum atom, or aluminum ion, which has a positive 3 charge versus sodium, which has a positive 1 charge. So that is going to influence it. Also, the size. So fluorine is a much smaller ion size, for example, than chlorine. So again, depending how far you can take this, you can actually calculate the distance between the different ions, but we are not going to do that here, okay? So anions are usually larger. We say that they gain electrons. Yes. A repeating pattern. Plus, minus, plus, minus, plus, minus, plus, minus. Okay? You might have, even if say you have a deck, and then some people call it lattice work underneath, and you get that repeating pattern. So there could be lattice work, which is a repeating pattern. In our case, for ionic, it's plus minus ions. Okay, cations and ions and anions, the same as we talked about yesterday. Okay, so the anions are usually larger because they gain electrons. We talked about that in grade 11. And when you lose electrons, even though it's a terrible, cheesy analogy, you can think of it like losing weight. They have a very high melting and boiling point. And the most common example is sodium chloride, that's table salt. Calcium chloride is road salt. Okay, so we have studied ionic solids, ionic compounds, ionic bonds extensively. Okay, so all of the same principles apply. Transferring electrons, the metal loses electrons to become positive, the non-metal gains electrons to become negative. So this is this is an example. There's the word lattice right there. So again, you can kind of see it's a bit cubic. Okay, so should you continue on, you can calculate the cubic structure. We don't need to do that. So if you have an ionic solid, it's going to be very hard and have a very high melting point. So last year we did a testing properties lab, and the ionic compounds had melting points like 618 degrees Celsius, very, very high. Due to the strength of the ionic bonds, they are very brittle, so they are, like if you have table salt, you could smash it, because we call the bonds directional, and that's your textbook uses that word to describe, because it's an attraction between plus and minus, it calls it directional. And as you know, once you dissolve it in water, it will conduct. So the presence of ions makes it conduct, but you have to dissolve it in water. Okay, so apart from the word directional, we have talked about this before. So try not to push out of your brain the ideas that you already know about ionic compounds, okay? Melting and boiling point. What's the boiling point? Let's see. I'll find a boiling point. Is there? Okay. I'll go back for a second just to make sure. Everybody good here? Okay. So then the last one is a metallic solid. Formed by metallic bonds, and I did say yesterday that there would be a picture today, which there is, okay? And I believe it's the same picture that we would have used in grade 11. So again, we talked about metallic bonds yesterday, we talked about them in grade 11. Don't push out of your brain things that you already know, okay? So you need delocalized valence electrons. So which kind of elements have that? That they are transition metals. And we said yesterday, metallic bonds are formed between transition metals. So you have the sea of valence electrons. They are totally weird, totally delocalized. not in Bohr orbits at all. So your textbook, because they're not plus minus, then it calls it non-directional. It is non-directional is defined, not the next slide, but the slide after. And just want to make sense, it basically is like no direction, no pattern, okay? One of the big things is they can conduct electricity because their electrons are mobile. Freely moving, which again is on not the next slide, the slide after. Okay, explained again. It was on yesterday's note as well, so it's up to you. Okay, so you have, even if your note doesn't have color, that's totally fine. It's more about that you have the positive, like the nucleus, and then the electrons are all over the place. Okay, they're not in Bohr orbits at all. So again, I really hope your teacher did not make you go past number 20. 21 is the start of the transition metals, and they have a very unique electronic structure. So delocalized electrons, they are mobile or free to move around, which is hard to show on a paper and pencil, or like a 2D picture. Sort of like a mobile home, right? It can move around. I know that's trendy these days. It's not stuck at one address, at one place. Same idea. So the next slide definitely explains that. Non-directional bonds are freely moving electrons. Which makes them able to conduct electricity, and it also makes them flexible. So that's why we can, they're ductile, we can pull them into a wire to make copper wiring. But there is still the plus minus a little bit. There's a little bit of an attraction, making or having the potential to be a solid. Okay, so on the note, it's okay if you don't have it. I did try to make a chart there. Now, what I want to do is try to summarize things as concisely as we possibly can. If you have really big handwriting and you're like, yeah, right, Ms. Todd, I'm never going to be able to fill out this chart, then what I would do is just get a piece of paper. There is some lined paper on my beige filing cabinet there because what I want to try to do is summarize it the best we can and as concisely as we possibly can. So we're going to go through the 5. Again, we're not going to worry about glass and rubber anymore. Okay, so atomic, molecular, network, ionic, and metallic. Molecular is the toughest because there is nonpolar and polar, but the other ones I think we'll be able to fit in the spot okay. No, I'm really trying to make it as concise as possible because really the note is kind of paragraphs, right? So let's summarize the ideas. So for atomic, then you have atoms. Whoa, do not use a highlighter. I did try to make the properties one the biggest. In the spot, so you could even write it in here as well if you want to write some examples. So we talked about noble gas atoms. atomic is dispersion forces. If you would like to remind yourself that they are weak, but maybe you're like, no, I got it, I don't need that, it's up to you. So because they have weak forces, then they have, and I'm going to use MP and BP. I hope that's okay. And they are not hard, or you can call them soft. I forget what the note says. But molecular, that's the tricky one, because you can have molecules, but as you know, there are nonpolar and polar molecules, okay? So nonpolar molecules will have London dispersion forces, whereas polar, you could actually kind of split them into two. So this is tricky. Yeah. You could really actually just write dipole, to be honest. Okay, so in general, they are not super hard, and they do not conduct. Now, it is sort of a little bit ruthless to ask you, to compare melting points within polar molecules. Now, when we get to organic, we're going to talk more about the difference between nonpolar and polar. So eventually you will be able to do it, but here that's a bit tough. Now, what you can do, if you wrote them like this, the same order I did, the melting and boiling point would increase as you go down, okay? But to be honest, that's a bit ruthless here. No. So for a network solid, as soon as you've seen carbon atoms by itself or silicon atoms by itself, again, that weird group, the plus or minus 4 that normally we would skip, let's start dealing with them. There is a sneaky question in the textbook for homework. They include silicates as well. But to me, that's sneaky. But your textbook is sneaky, I won't lie. So let's include it in there, okay? The force is covalent. Which, if you want to remind yourself, it's very strong. So these are hard, very high MPBP. What else do you want to say? Good. Conductive. Don't conduct? No, I don't know. We'll make up words. That's fine. So for ionic, you can put ions, you could put metal and non-metal, you could put cation and anion, which we did yesterday. You kind of, there is a variety of ways to describe these. Which means it's an ionic bond. So again, these are also very strong, which maybe you know, right? So um, no, it would be like multiple choice. And I would try to pick super obvious ones, like what kind of, what's in an ionic bond, which you would have known in grade 11, probably even grade 10, really. Maybe this one because it's unique, but again, it's so weird that it's kind of like you do one question and you're like, all right, I get it. So because metallic solids have metallic bonds are transition metals. So like I was just asked, we have talked about that before. So don't push out of your brain things that you already know. Metallic bonds are very strong, but they do have a high melting and boiling point, but they do have that weird electronic structure. So they are flexible and they will conduct. So that is a difference between ionic and metallic. So it's important to not just put metals, put transition metals. Okay? So these things that we've written down would have been things we highlighted. Okay? It's just another way to summarize it. So the worksheet, we're going to do the other example, which will help you with the textbook questions. But the worksheet is about properties. Now, I got this worksheet from somewhere. It's trying to be, I don't know, it's just a different way of thinking of things, to be honest. So what you're going to do, it's like categories. So the categories are at the top. It says particles and crystal. So what you do is you go to the particles in the crystal and read the statements and decide which ones apply. It does split apart polar and nonpolar, so that's helpful. And then you put the number that applies to that solid. Then you go to the next category and the next numbers, and it says check your work. The numbers in each row should add up to 126. So, it's just a different way. I put the answers online as well. So this will help you with the properties. The textbook questions will be more questions like this. If you are given a specific element or compound, what is going on? Okay? So, what kind of element is xenon? It is a noble gas. So, we just summarized that. It's a noble gas. It's an atom all by itself. So then it's going to be an atomic solid. It doesn't ask you to explain, but I'll put it in brackets, okay? And then you can use the chart we just filled in to help you. What kind of forces are in atomic solids? Good. So really unique to this, to chemistry, this may be a case where to study for the test you'd like to make cue cards or some way to help you memorize. That's not often what you have to do. Now, again, some of the solids like metallic and ionic we've talked about before, that kind of bonding. So don't push out of your brain things you already know, okay? And even when you get a question like this, let's say you get to this one and you're not entirely sure. Then go to the next one, carbon. Is carbon special? Does it make a special type of solid? Yes, right? This, copper. What kind of metal is copper? Transition metals. They make a special kind of solid. What is this? Sodium chloride. Metal and non-metal. Ionic, right? They make a kind of solid. And then you can think about this. Okay, the only one left is molecular. Okay? Now, this is also something special. What is iodine? I2. Why is it I2? Yeah, and we call that something. Good. A diatomic molecule. And then you're like, oh yeah, okay, that's a molecule. That's molecular. Now, molecular is nasty because if you have to state the type of force, then you have to figure out, is it nonpolar or polar? And again, we reviewed that yesterday. Just do the change in electronegativity. Now, this is two of the same thing, so it's automatically going to be 0, but you could definitely just go and do it. And if it's nonpolar, what kind of forces does it have? I heard someone say it. So I would say that molecular is the nastiest. Yes, and you could actually write London. You can write London dispersion. All of that would be the same. It is the nastiest because the molecular has different categories. Okay? So this is carbon. So when you have carbon by itself, like there's no H, there's no, like it's not methane, it's just carbon. So the carbon atom, what kind of solid will this form? This, yep, network. Which is covalent. Whoa, brain fart there. Okay, and then again, what kind of metal is copper? It's a transition metal. And even if you forgot what sodium chloride was, you could also do the change in electronegativity. You always, always, always get that copy of the periodic table. You could definitely do that. Now, sodium chloride is probably in grade 9, the first ionic compound your teacher talked about. So again, try not to freak yourself out. Try to not push out of your brain things you already know, okay? I can even write it down if you want. Because that really is a foolproof way. For ionic, it has to be a metal and a non-metal. You could have molecular, like you could have CH4, H2O, but those are non-metals. Okay, so your textbook is questions sort of like this one, and then the worksheet is more about the properties. So use that summary chart to help you. Okay?